Hello students, welcome to Aditya Academy. I'm Dr. Ragini Arora, and in this video we will be continuing from question number 17 to question number 25 of exercise 14.1 from NCERT. So the question number 17, the first part says a lot of 20 bulbs contain 4 defective ones. One bulb is drawn at random from the lot. What is the probability that this bulb is defective? So the total number of bulbs here is 20 and the defective ones are 4 in count. Out of 20, 4 are defective. That means the good ones become 20 minus 4, 16 in number. Right? So the total number of bulbs is 20. And out of those, a out of 20 bulbs contain 4 defective ones. If 4 are defective, that means 16 are good in quality. Now they have drawn one bulb. They have drawn one bulb from that lot. What is the probability that this bulb is defective? Defective, right? So for that we need to write number of favorable outcomes upon total number of outcomes. In this experiment we have favorable outcomes. For a bulb to be favorable, it has to be defective in this case. So we have 4 defective bulbs. So favorable are 4 and total number of outcomes are 20. So we get 1 over 5 as the probability of drawing a defective bulb from the lot of 20 bulbs. Next part says, suppose the bulb drawn in part 1 is not defective. Right? So probability, that means we have drawn a good bulb. What is the probability of good bulb here? The good bulb is probability of good bulb is favorable are 16 and total are 20. So it is 4 4s are 16, 4 5s are 20, 4 by 5. And total good bulbs are 16 in count. He says, suppose a bulb drawn in 1 is not defective and is not replaced. That means if we have drawn, now the total number of bulbs in the lot becomes 19. Since we have drawn one bulb out of that lot and we have kept it aside, we have not put it back into the lot. So the total number of bulbs in the lot becomes 19. And since he says the bulb that we drew in the last question is not defective. Not defective means it was the good one. So earlier we have good ones were 16 in number. So now one good bulb has been removed. So the good ones become 15. Now how many are there which are defective? We still have 4 defective ones because all the defective bulbs are still lying into that lot. We drew one bulb from the lot and that was a good one. So the good one has been reduced by one number. The total one has been reduced in one number and the defective ones are still there in the whole lot. Now he says, now one bulb is drawn at random from the rest. Now we are left with 19 bulbs, out of which 15 are good and 4 are defective. So what is the probability that this bulb is not defective? Not defective means we are drawing a good bulb now. So now the favorable outcomes, number of favorable outcomes upon total outcomes, right? The good ones are 15 in count because there were 16 bulbs earlier and the one which we had taken out in the previous experiment has been taken out and put aside. We have not put it back into the lot. So the good ones are 15 in count and in the total we have been reduced with one bulb which has kept aside. So the probability of drawing a good bulb in this case becomes 15 by 19. Next question is, a box contains 90 discs which are numbered from 1 to 90. If one disc is drawn at random from the box, see this box has discs which are numbered from 1 to 90. So like 1, 2, 3 up to 10. Then we have 11 to 20 and up to this like 90. So we have, in all we have 90 discs, right? The total number of discs is 9090. If one disc is drawn at random from the box, find the probability that it bears a 2-digit number. Now let us calculate how many 2-digit numbers are there in all in these 90 discs. Let us say we have numbers from 1 to 90, in which we have only 1 to 9 as 1-digit numbers. So out of 90, only 9 discs are having 1-digit numbers. That means 90 minus 9, 81 discs have 2-digit number. Because after 9, all the digits are 2 digits till 90. So if we subtract these 9 1-digit numbers from 90, we are left with 81 2-digit numbers. 2-digit numbers here are 81 in count. So when we are finding the probability of a 2-digit number, number of favorable outcomes upon total outcomes. Number of favorable outcomes here is 81 and total outcomes are 90. So this becomes 9 9s are 81, 9 10s are 90. This is 9 by 10. Second part says a perfect square number. So now I'm just writing all the favorable outcomes here. Perfect square number. So if we start with 1, 1 itself is a square of 1, which is a perfect square. Next we go for 2. Square of 2 is 4. Square of 3 is 9. Square of 4 is 16. 5 square is 25. 6 square is 36. 7 square is 49. 8 square is 64. 9 square is 81. And then 10 square is 100. Now 100 is not there. We have discs which are up to 90. So 81 is the largest square number which we can include till 90. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 perfect square numbers in the given sample space. 9 perfect squares. So the probability of a perfect square is number of favorable outcomes upon total outcomes. Favorable outcomes here are 9 in count and total outcomes are 90 in number. We have 90 discs, so it becomes 1 by 10. A number divisible by 5, right? So how can we find this? A number divisible by 5 is 5, 10. We can have a list of numbers 5, 10, 15 and then 20. This way we can go up to 90. The last number 90 is also a multiple of 5. So here we have to use, instead of finding all these multiples by writing all these numbers, so we have 10. 2 multiples in the first row from 1 to 10. You can go this way also. 15, 22 in the next. And since we have 9 rows, 1 to 10, 11 to 9 rows, so 9 twos are 18, right? So multiples of 5 are 18 in count. You can divide 90 by 5. So we have 18 numbers which are divisible by 5 here. One more method you can apply. This is an AP. This sequence is an arithmetic progression. So the first term here is 5. the last term here an is 90. If you have to count how many terms are there in this sequence, an is equal to a1 plus n minus 1d. An is, last term is 90, first term is 5. N we have to find, and common difference here in this sequence is 5. So 90 minus 5 is 85. 85 is 5, n minus 1. This 5 goes here to 17 is equal to n minus 1. So n becomes 17 plus 1, 18. So there are different methods, but make sure that you are not making, generally children make mistake in such kind of questions. That is why make sure the way you calculate it, you are not either adding one more or leaving any number out of that sequence. So the number of terms or favorable outcomes in this case is 18. So when we find the probability of a number divisible by 5, number divisible by 5, or a number being a multiple of 5. So favorable outcomes, number of favorable outcomes upon total outcomes. We have 18 favorable and total is 90. It is 1 by 5. Next question is, a child has a die whose 6 faces show the letters as given below. You can see that this is a biased die. That means generally we always have seen a die which contains numbers from 1 to 6. Now this die has got 6 faces, but they have these biased numbers. A is occurring twice, B, C, D, E are occurring once. So we call it a biased die. The die is thrown once. What is the probability of getting A? Right? So probability of getting an A is number of favorable outcomes upon total outcomes. So that is, favorable outcomes are, how many are there? We have 2 A's out of 6. So favorable outcomes are 2 and total outcomes are 6. So the probability of getting an A is 1 by 3. And probability of getting D is favorable outcomes upon total outcomes. For D, we have only one value, one elementary event. Favorable outcomes are 1 and total outcomes are 6. So the probability of getting D will be 1 by 6. So the next question says, suppose you drop a die at random on the rectangular region shown in this given figure. What is the probability that it will land inside the circle with diameter 1? So in this figure, diameter of the circle is, the rectangle has length 3 meters and breadth 2 meters. So this circle has diameter 1. So the radius becomes half. Right? Now he's asking the probability that you drop a die at random. This is an area made on a paper, let's say. And if you are throwing a die on that paper, what is the probability that die will land inside this circular region? This circular region. So for that, we have, first of all, we have to find the area of rectangle. So that is the total area on which we are allowed to place our die. Area of rectangle is length into breadth. Length is 3 and breadth is 2. The total area becomes 6 meters square. Right? And then diameter of circle is 1 meter. So the radius of circle becomes half meter. And area of circle becomes pi r square, right? Pi r square means we keep pi as it is. I'm not going to substitute the value of pi as 22 by 7 or this. Keep it in terms of pi, it is a constant. Radius here is 1 by 2. So the square of this becomes pi into 1 by 4. So pi by 4 is pi by 4 meter square is the area of circle, right? This is the whole area on which we can throw our dice. This is a whole area. And if we have to find the probability of falling that die being falling into this exact region, is the probability of die in a circle is favorable outcomes upon total outcomes. Here, favorable outcome is the die being falling into the circular region. So the area of circular region is the favorable region. So I'm writing the area of circle in the numerator, and total area of the whole region is the area of rectangle. That means it is 6. So when we solve it, we get pi over 4 by 6. The probability becomes pi by 24. Right? Next question is, a lot consists of 144 ball pins, of which 20 are defective and the others are good. A lot consists of 144 ball pins. So the total number of ball pins is 144, out of which 20 are defective. Defective are 20. So the good one becomes 144 minus 20. So 124 are good. Noori will buy a pen if it is good, but will not buy if it is defective. The shopkeeper draws a pen at random and gives it to her. What is the probability that she will buy it? So the probability of Noori buying a pen means the pen is good one, right? The probability of good pen. Indirectly we can say she will buy it means this pen is good. The probability of good pen is number of favorable outcomes upon total outcomes. Favorable here, good ones are 124 in count, and total number of pens are 144. So when we divide it, 31, 4 3s are 12, 4 1s are 4, 4 3s are 12, 24, 4 6 are 24. So the probability that Noori will buy that pen is 31 on 36, because in that case it will be a good pen. And the second part is she will not buy it. That means the probability of pen being defective. So we can solve it in two different ways. Either we can find the favorable outcomes, means we can simply write the bad ones in the numerator, because favorable are defective ones. Defective are 20 out of 144. 4 5s are 4, 36 are. It is 5 by 36. Or other way you can say that they are complementary events. So complementary events means probability of defective is equal to 1 minus probability of the pen being good one. This is 1 minus 31 by 36. It is 5 by 36. The pen will be defective. This is a complementary event to pen being good one. So we can find it this way or this way. That this question is exactly linked with example 13, in which we have to find the probabilities of sum on sum when two dice are thrown. So here, first of all, I am making a sample space for two dice, that is 1 1, 1 2, 1 3, 1 4, 1 5 and 1 6. 2 1, 2 2, 2 3, 2 4, 2 5 and 2 6. This is 3 1, 3 2, 3 3. In case of two dice, we get 36 elementary events. 4 1, 4 2, 4, 3, 5, 1. In this example, the table was not completed, and I will tell you how to fill this table. 5, 4, 5, 5, 5, 6. The last row is 6, 1, 6, 2, 6, 3, 6, 4. These are 36 elementary events in the experiment of throwing a pair of dice. Now, see, we are trying to find the sum of digits on two dice, right? The sum, since the least number on each die is 1, so the sum will start from 2. The first sum is 2. In how many ways we can get the sum of two dice as 2? This is the only favorable outcome. 1 on both dice gives us the sum 2. There is no other option which gives us the sum 2. So out of 36 we have only one favorable event which is giving us sum as 2. Now sum as 3. You can see sum 3. So I'm marking here this 2 plus 1, 2 comma 1. This is then this is 2, 2 1 and 1 2. 1 2 and 2 1 are two elementary events which give us the sum as 3. So the favorable outcomes are 2 out of 36. So the probability of getting a sum 3 becomes 2 by 36. In case of 4, we have to get the sum 4. You can see this is 1 3, 1 3, and this is 5 6. Then we come to this 2 2, 2 comma 2, and this 2 3 is 3 1, 1 3, 3 1, and 2 2. These three elementary events are giving us a sum 4 on a pair of dice. Similarly, we can complete the table. This is 5. Sum 5 can be, you can get 5 from here, you can get 5 from here, 3 2 here from here, 2 3, 3 2, and this. So we have 1 2 3 4 favorable events. 4 favorable events out of 36. So this is 4 by 36. The probability of getting a sum 5 is 4 by 36. Similarly 6. For 6 you can check. I'm just making a rectangle over this. This is 1 5. Then for 6 it is 2 4. Right? Then in the next row 6, we are getting 6 from here, 3 3. We go here, this is 6 4 2, right? And this is 5 1. So in these 6 different elementary events, 1 2 3 4 5, we have 5 elementary events, 5 favorable events in which the sum is 6. So the probability becomes 5 by 36. Similarly, we can complete the whole table. You can see here the sum 10. 10 we can get in the first row, the maximum sum is 7. It is 8. It is 9. When we talk about 10, this is sum 10. The next row we have 5 5 to give us 10. Then we have 6 4 to give us 10. So we have 3 elementary events corresponding to the sum 10. So the probability becomes 3 by 36. Similarly, for 11, we have 5 6 and 6 5. Only 2 elementary events. Probability is 2 by 36. And the 12th one is sum 12. It's only one elementary event which is providing sum 12. So probability becomes 1 by 36. Now the question says that we have 11 different values. The values of sum can be is starting from 2 and moving up to 12. So we have 11 different outcomes. But you can see from the probabilities that though the different values for sum are 11, but their probabilities are not equal. So they are not equally likely possible. They are not equally likely possible outcomes. Since the chances of different sums are different, So the probabilities are different, hence they are not equally likely possible events. So the statement is not justified. Next question says, a game consists of tossing 1 rupee coin 3 times. So first of all, here we have to write the sample space for 1 rupee coin 3 times. Head, head, head. First we have 2 heads and 1 tail in different orders, then 2 tails and 1 head in different orders. Tail, tail, head, then head, head, tail, tail, and finally we have 3 tails. 3, 4, 5, 6, 7, 8. So we have 8 elementary events in the sample space of this random experiment. A game consists of tossing 1 rupee coin 3 times and noting its outcome. These are the possible outcomes in case of tossing 3 coins or tossing 1 coin 3 times. Both means the same thing in this. Hanif wins if all the tosses give the same result, that is 3 heads or 3 tails, and loses otherwise. So for winning, favorable outcomes are either all the 3 heads or all the 3 tails, and loses otherwise. Or for losing we have rest of the 6 outcomes: 1, 2, 3, 4, 5, 6. Calculate the probability that Hanif will lose the game, right? So probability of Hanif losing the game. So for losing, we have to write favorable outcomes, number of favorable outcomes on the numerator and total outcomes in the denominator. For losing, we have 6 different possibilities because for winning we have only 2, and out of 8, these 6 outcomes give us the result of Hanif losing the game. So the favorable outcomes for losing are 6 in count and total outcomes are 8. So the probability of Hanif losing the game is 3/4. Right? Next question is, a die is thrown twice. What is the probability that 5 will not come up either time? So for now this, I'm going back to the sample space that we had done in question number 22. 5 will not come up either time. See, in this sample space, how many elementary events are there in which there is no 5 on both the dice? 5 will not come up either time. So leaving this, I'm using a different colored pen here. You leave this here, right? So we are left with 5 in the first row, which does not, 5 elementary events in the first row which doesn't have any 5. In the second, you leave this. Again, we have 5. The third, you leave this. We have 5. For 5, you leave this. We have 5. And in this row, we have to leave the whole row because the whole row contains at least 1 or 2 5s. And in the last one, leaving this, we again have 5 elementary events which correspond to the requirement of not having 5 on any of, see, 5 will not come up either time. So the probability of 5 or 5 will not come up either time. Not having 5 on either of the dice. So we had 25 such cases. You can leave this whole column and this row. So you can count here, 6 are here and 6 are here, 12, but this is common, so minus 1 is 11. So out of 36 you can subtract 11. So 25 elementary events are there in which there will be no 5 on either of the dice. So the probability of this P not 5 on either dice is 25 over 36. Now the second part says 5 will come up at least once. Probability of 5 at least once. At least once means minimum 1 and maximum we can have it on both the dice. So if we go back and say 5 at least once. So these are the circled rows and columns. In this one we have 5 at least once. See, this is the vertical column in which we have 5 on the second dice throughout this column. And in this row we have 5 on the first dice in this row. So 6 here and 6 here. We have 12, but this number is common to both, so minus 1. We have 11 such elementary events in which 5 is occurring at least on one die, or in this case it is occurring on both. So we have 11 such events. So now the question says 5 will come up at least once. At least once, or maximum we can have twice. So there are 11 favorable outcomes and total we have 36. So the probability of 5 coming up at least once is 11 by 36. This is the last question, which says which of the following arguments are correct and which are not correct. Give reasons for your answer. If two coins are tossed simultaneously, there are three possible outcomes: two heads, two tails, or one of each. Therefore, for each of these outcomes, the probability is 1 by 3. So this is a similar kind of question that we have to justify. First of all, I am making the sample space. If two coins are tossed simultaneously, the sample space becomes head, 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 tail, tail, head, and tail, tail. He's saying if two coins are tossed, there are three possible outcomes: two heads and two tails. But if you see exactly, when we are tossing two coins, we can end up with having two different outcomes in which we have exactly one head and one tail, but they are different in order. We can have first head and second tail, or first tail and second head. But since both of them give us the exact answer, like one head and one tail, so we cannot say the probabilities of two heads, two tails, and one head are same. We have four different possible outcomes in this experiment. So here every elementary event has a different probability. This is which is not equal to 1 by 3. So this statement is not justified. If two coins are tossed, two heads, two tails, or one of each. So one of each, we have two different outcomes for that. Therefore, for each these outcomes, the probability is 1 by 3. This is false. We can see that for probability of two heads are occurring only once out of 4 elementary events. So this is 1 by 4. Probability of one head. For one head, we have two different outcomes. One head can occur head and tail, or tail or head, in different orders. So the probability becomes 2 by 4, which is 1 by 2. And the probability of getting exactly two tails is again 1 out of 4 total outcomes. So we can say that the probability, saying that every outcome is having the same probability as 1 by 3 is false. Next question says, if a die is thrown, there are two possible outcomes: an odd number or an even number. Therefore, the probability of getting an odd number is 1 by 2. Now this we may check with the sample space. 1, 2, 3, 4, 5, 6. So before making a statement like this, you always should go by the sample space and then check whether all these events are equally likely possible or not. In the previous example, the events were not equally likely possible, which he was expecting that two tails, two heads, and one each. They are not equally likely possible because we have two heads and two tails, but in case of one head or one tail, one each, they have different two events which are different in order. So the probability is never 1 by 3 because the events are not equally likely possible. We can write here not equally likely possible. So we have to look for, in the case of dice also, the sum where we had done question number 22, the sum from varies from 2 to 12 and all the sums have different probabilities, so they were not equally likely possible. But in case of equally likely possible, we can check in the next sum. This is the sample space for a dice. Out of this, the odd numbers are 1, 3, and 5. And even numbers are half in count 2, 4, 6. So you can say in both the cases we have three favorable outcomes in case of odd numbers and in case of even numbers. So even and odd are having equal possible outcomes. They are equally likely possible. Equally likely possible. So if we find out the probability of an even number, it is 3 by 6, which is 1 by 2. And if we find the probability of getting an odd number, it is also 3 by 6, which is 1 by 2. So in this case, we can say that this statement is true. Right? So this was all from this exercise 14.1. We have covered all the questions in this video. I hope you liked watching this video. So please subscribe, like, and share it with your friends. Thank you.